Hello and welcome to Mr. Tompkins EdTech. This series of videos provides work solutions for the GCSE Maths Topic Test produced by AQA. This video is Factors and Multiples. Whilst these topic tests make excellent exam preparation and revision material, regardless of which exam board you're sitting, they are particularly useful for students studying for AQA as they are prepared by the same team who will be writing your papers in the summer. They will work best if you try and answer the questions yourself before watching the video. The topic test papers can be downloaded from this address, which I've also linked in the description below. They'll require a teacher account to access, so either ask your maths teacher to download and share them with you, or alternatively you can try pausing the video and attempting the question first before pressing play again to listen to my solutions. Check this playlist for all the other topics I've covered. I'm busy recording all of these topic tests, so if the particular topic you're looking for isn't there yet, why not drop me a comment below with your request and subscribe to my channel to receive notification of future uploads. If there is anything you don't understand, please ask in the comments. Make sure you mention the question number and try to be as specific as possible. I try to answer all questions promptly, especially around exam times. If you found the video useful, please do hit the like button, as this really helps me out. You might also like to check out my exam paper walkthroughs covering all the recent papers and practice papers from AQA. Just click on the card appearing at the top of the screen now. Okay, let's get started. Welcome along to another AQA topic test. This one is for factors and multiples, and it's listed as a higher topic, but many of these questions would also come on the foundation paper. Before we get started, I'm just going to show the blank question paper. So if you don't have a copy, you can now pause it and have a go at the questions first, and then once you're finished you can start again and look at the answers. Okay. Question 1. I've got two numbers, x and y, and they've been given as a product of their prime factors. So I've got 3 squared times 5, that's x. Well, 3 squared is 9 times 5 is 45, so x is 45, but it's written down as a product of its prime factors. And y is 2 times 5 squared. 5 squared is 25 times 2 is 50, so y is 50, but again it's just been written as a product of its prime factors. Okay, so circle the lowest common multiple of x and y. Okay, now I suppose you could do what I just did there, multiply those out. 9 times 5 is 45, and 2 times 5 squared, 25, 50. 45 and 50, you could start listing multiples of both of those numbers until you reached a common one. That's what you tend to do when you're just given two numbers and asked to find an LCM. But there is another way of doing it, and it's and as these numbers have both been given as products of their prime factors already, it's probably quicker to use this method than the one I just suggested. Okay, so the method for finding lowest common multiple from products of prime factors is quite simple actually. What you do is you look at both your numbers in prime factor form and you read off every base that appears in either numbers. So when you've got a number with a power, so like 2 to the power 3, then that 2 is the base and the 3 is the index. So I'm talking about the big numbers in either of these two numbers. So if you look at x, it's got bases of 3 and 5, and y has got bases of 2 and 5. So altogether there are 3 different bases appearing, 2, 3 and 5. So I'm just going to write them down like that, and I'm going to multiply them together. Okay, I'm not quite finished yet as well. So to find the LCM, you need to take out every base that appears in either of those numbers to the highest power it appears. Okay, so the 2 only appears once. It appears in y and it has a power of 1 in that expression. The 3 only appears once. It appears in x and it has a power of 2 in that expression. Now the 5 appears in x and it appears in y. In x it has a power 1, in y it has a power 2. We write down the highest power that appears in either of them. So I'm going to write down the higher one of those two, it's 2. Okay, so my LCM then I can get by multiplying that out. So time to reach for the calculator. I'm just going to tap that in. So 2 times 3 squared times 5 squared, what's that then? 450. 450. So it's that one there. Now, question 2A says, write 280 as a product of its prime factors. Okay, now the method I would suggest you do this would depend on whether or not it's a calculator or a non-calculator paper. Let's just do it the non-calculator way first. For a non-calculator paper, I would use a factor tree. So I start off with the number I'm given at the top of the tree, and then each number you then branch off in two different directions, and then you think of two numbers that multiply together to give you 280. It doesn't matter which ones you pick actually, but the first ones that popped into my head was 28 and 10. 28 times 10 is 280. I'm going to put circles around those. Now if they're prime numbers we can stop, but if they're not we have to keep trying to break them down further. So 28 is not a prime. So I'm going to break it down. So 28 is what? It's 2 times 14. So I'm going to write a 2 there and 14 there. Okay, now 2 is prime, so I can stop on that one, but 14 isn't, so I'm going to break that down a bit further. 14 is 2 times 7. Now 2 is prime and 7 is prime, so they're both stopping points. Let's just follow down the other branch. 10 is 2 times 5, so I'm just going to write 2 and 5 there. Okay, and they're both prime, so I can stop on those. So 280 written as a product of its prime factors is all those terminating leaves written one after the other. So I've got a 2, a 2, and a 2, so 3 2s. 2 times 2 times 2, and then I've got a 5 and a 7 times 5 times 7. And you might just want to multiply that out in your head just to make sure you do get back up to 280. Sometimes these questions ask them to write it in sometimes these questions ask you to write your answer in index form. It doesn't here, it just asks you to write down as product of its prime factors. So this answer is perfectly acceptable. But if it did ask you to do it in index form, then you would just rewrite this as in their power form. So 2 times 2 times 2 is 2 cubed. It'd be 2 cubed times 5 times 7. Now if you're lucky enough to have a fairly recent Casio calculator like this one, you can actually do it in one calculation. It's very easy to do on one of these calculators. I'm just going to type in the number 280 and press equals. So 280 is the calculated value. And then I'm going to press shift and then this key that says fact on the top, short for factor I suppose. So if I press that, you'll see that it immediately rewrites it in that form that I've just worked out. So 2 cubed times 5 times 7. So if it's a calculator paper, just tap the number in and press that button, job done. Non-calculator paper, use a factor tree. Okay, now part B says 588 is 2 squared times 3 times 7 squared. And we're asked to work out the highest common factor of 280 and 588. Now there's actually another trick to find in HCF's highest common factors using prime factor decomposition form of numbers, a bit like we did with the LCM earlier. For this one it's easier if you have the number written out in its expanded form, so without the powers in. So I'm just going to rewrite 588 in expanded form. So 2 squared is 2 times 2, I'm just expanding out all the powers, times 3, and 7 squared is 7 times 7. Okay, now you remember from the last question, 280 was 2 times 2 times 2 times 5 times 7. Now the way you find a HCF, highest common factor, from numbers written in this form is what you need to do is pair up numbers that appear in both expressions. So I've got a 2 there which goes with that 2 there. I've got a 2 there which goes with that 2. My 3 doesn't match with anything. My 5 doesn't match with anything. I've got a 7 there which can match up with that one there. So I've got 3 and 7 left in 588, and I've got a 2 and a 5 that I can't pair up with anything in 280. So anyway, what we do now is we take each of those numbers that I did ring and add that into our HCF expression. So that's 2 times 2 times 7. Okay, so what is 2 times 2 times 7? 4 times 7 is 28, isn't it? Okay, so my HCF is 28. Okay, so using prime factor decomposition, there's a technique for finding both the HCF and the LCM of a number. Question 3. A, B, and C are different prime numbers. Work out a set of values for A, B, and C so that A plus B is equal to 2C. Okay. Where do we start? It's a bit tricky, this one. I think probably what we want to do is just maybe list out some of the primes. Okay, so what are the primes? The first prime is 2, 3, then 5, then 7, not 9, 11, 13, not 15, 17, 19. Let's just stop there and see if we've got any that we can make work for this. Probably easier to do with the lower numbers than the bigger ones. So can I add two numbers together and make a double another? Well, it can't be the 2, can it? Because 3 plus any of the other primes plus 2 would be odd, and we're looking for an even number. So we want to be adding 2 odd primes together and getting double another prime. Okay, so let's think about 3. 3 and 5 makes 8. That's not double a prime. 3 and 7 makes 10. Oh, 3 plus 7 is 10. That's double 5, isn't it? So 3 plus 7 is equal to 10, but 3 plus 7 is equal to 2 lots of 5 then, isn't it? Okay, so A is going to be 3, B is going to be 7, and C is going to be 5. That works. Okay, there might be other solutions, I don't know, but we found a solution, and it just says work out a set of values that works, which is what we've done. Question 4. A number is an odd multiple of 3 and a common factor of 180 and 750. Work out the greatest possible value of the number. Again, here it's not so obvious about where to start in this question. You know, sometimes you just got to get stuck in really with these sort of things and try something out. I'm not quite sure how to do this question myself. I'm just gonna do some stuff and see if it helps. So I'm going to start off with 180, and I'm going to find the factors of 180, I think, and that will give me some fuel to then work with the other facts I've been given. So let's have a look at 180. So factor pairs of 180. I've got 1 and 180. I've got 2, which goes with 90. 3 goes into 180, doesn't it? 3 times 60. Does 4 go in? Yes, it goes in 45 times. About 5. 5 does, ends in 0, so it must be divisible by 5. So 180 divided by 5, 180 divided by 10 is 18, so double it is 36, isn't it? Are we done? I don't know. Let's keep going. 6, it's got lots of factors, this thing. 6 is, yeah, that goes in, doesn't it? Because 6 goes into 18 3 times, so it must go to 180 30 times. 7, I'm doubting 7 will work. What about 8? 80, 140, yeah, 8 might work. 8 times what? So 8 times 10 is 80, then 160, no, it doesn't work, 9, yep, 9 does. 9 goes into 18 twice. It must go into 180 20 times. 10, yeah, 10 goes with 18. 11, no, I don't think so. 12 might work. 12 goes into 120 10 times, and 65 times. It must go into 180 15 times. So we're getting close now. 13, I don't think that's going to work. 14 doesn't go work, and then I've kind of met myself coming back down the other way. So they are all the many factors of 180. Okay, so I suppose we want to rule out any ones that are not odd multiples of 3. because they aren't meeting the first condition. So I'm going to scratch out any that are not multiples of 3. So 1 isn't and 2 isn't. 3 is a multiple of 3, yeah, so that's a possibility. 4 isn't, 5 isn't, 6 is a multiple of 3, but it's an even multiple, so not that one. 9 works, 10, no. 12 is 3 times 4, it's an even multiple of 3, so not that one. 15, that's 3 times 5, that works. 18, that's 3 times 6, so no, that's an even multiple of 3. So actually we can just get rid of all the even numbers, can't we? And just check the odd ones. So 45, is that a multiple of 3? It is. It's 3 times 15, isn't it? So I've got 1, 2, 3, 4 of those factors of 180 that fit the bill. So now I just need to see which ones are factors of 750. Now I want the greatest possible one, so I'm going to start at the top of the list and work downwards. So does 45 go into 750? Well, a little bit of checking, probably you'll find that it doesn't. So it's not that one. What's the next one to try? 15. Is 15 a factor of 750? Now that looks like a possibility. 15, 150, 300, 600, 750. Yeah, that works. So 15 times, what is it? Times 10 is 150, times 20 is 300, times 40 is 600. So it's times 50, isn't it? 50 times 15 is 750. So 15 works as a common factor of 750, and we've said that 15 times 12 is in 180, and is it an odd multiple of 3? 3 times 5 is 15, so it meets all of the conditions. Okay, so that is the answer then, isn't it? It's 15. Question 5. We're given x as 2 squared times 5 squared times 11 to the power 4. We need to circle the square root of x. Okay, so we want to know what the square root of x is. So the square root of x has got to be the square root of that prime factor decomposition version of x we were given earlier. And if you remember your laws for surds, if you've got the square root of something like that, you can break it up into separate square roots. So the root of 2 squared plus 5 squared plus 11 to the power 4 is the same thing as the square root of 2 squared times the square root of 5 squared times the square root of 11 to the power 4. So what is the square root of 2 squared? The square root of 2 squared is just 2, isn't it? And the square root of 5 squared is just 5. So what's the square root of 11 to the power 4? Well, 11 to the power 4 square rooted is the same thing as 11 to the power 4 to the power of a half, isn't it? Because the square root of something is the same as the power of half. So you've got an index of an index. You can deal with that by multiplying those two together. 4 times a half, which is, well, it's just 11 squared, isn't it? And 11 squared is 121. So that last one there is 121. So it's 2 times 5 times 121. 2 times 5 is 10, and 10 times 121 is 1,210. So the answer's got to be that one there. Question 6. A and B are two numbers between 0 and 100. A is a prime number, and B is 3 times A. We want to work out the smallest and largest possible values of A and B. Okay, again, one of those questions where you're just going to have to kind of make a start somewhere. So let's just think this through. A is a prime number, so I could start listing the primes like we did earlier. 2, 3, 5, 7, 11. Where would we stop? If you think about it, A is a prime number and B is 3 times A. So B has got to be between 0 and 100, just like A does. So if I take 100 and divide it by 3, that's about 33 and a bit, isn't it? So my value of A has got to be less than 33, or no bigger than 33, I suppose. So I'm just going to list all the primes up to, but not over 33, because 34 times by 3 is more than 100. Okay, so 11, 13, 17, 19, not 21, 23, 25, nope, 27, nope, 29, yeah, it's prime, 31, yes, 33, no. So I think they're all the primes up to 33. So A could be any of those numbers there, I suppose. So work out the smallest and possible and largest possible values of A and B. So I suppose the smallest possible value is when I take my smallest possible prime, isn't it? So my smallest possible prime is this one. So if A is 2, that would make B 3 times A. B would be 6. So then A plus B would be 2 plus 6, which is 8. So that is the smallest possible value of A plus B. And then I suppose the largest possible value of A plus B is going to be if I took the other end of the list. So this one up here, the 31. So if I let A equal 31, then B would be 3 lots of 31. B would be 93. And then A plus B then would be 31 plus 93, which is, what's that, 124? 124. Okay. Question 7. Which of these is not a square number? Circle your answer. Okay, well, if you've got a square number, then the square root of that number must be a whole number. It must be a nice number. So we're looking for numbers that square root nicely, and they're not the one. No, we're not looking for the numbers who square root nicely. So let's go through the list. Let's start the one at the end first. 2 squared times 3 squared times 5 squared. If I take the square root of that, it's similar to that question I did just a moment ago, isn't it? So I can just take this, break that square root up into the root of 2 squared times the root of 3 squared times the root of 5 squared, which will just give me 2 times 3 times 5. Okay, 2 times 3 times 5, that's 6 times 5 is 30, isn't it? So that is a nice number. It's a whole number. So 30 squared is that number above. That makes 2 squared times 3 squared times 5 squared a square number, and so not the one we are looking for. Okay, so if I can square root it nicely, then it isn't. Then it is a square number and not the one I'm looking for. So let's have a look at 2 squared times 5 to the power of 4. 2 squared times 5 to the power of 4 is what? Well, I can just do the same thing, can't I? If I find the root of that, 2 squared times 5 to the 4, that's going to be 2 times 5 squared. 5 squared is 25 times 2 is 50. So that one is also got a nice square root. So it must be a square number. Now these ones not so easy because they've got a power 3 behind them. What can we do here? Well, if you think about 2 squared times 4 cubed, that's the same thing as 2 squared times 4 squared times 4. So if I take the square root of that, then the square root of 2 squared is 2. The square root of 4 squared is 4. What's the square root of 4? Square root of 4 is just 2. So 2 times 4 times 2 is 16. So that one is a nice square root. So it's not the one we're looking for. So it must be this one here by a process of elimination. Question 8. A menu has 8 starters, 6 main courses, and 6 desserts. Beth wants a starter and a main course. Chen wants a main course and a dessert. How many more possible combinations can Beth have than Chen? Okay, so for Beth, then the number of combinations of her meals, she can have any of the 8 starters, and she can have any of the 6 main courses. So she's got 8 times 6 possibilities. 8 sixes are 48. For Chen, he has got 6 choices for his main course and 6 courses for his dessert. That gives him 36 different combinations. So how many more possible combinations can Beth have than Chen? Then that's going to be 48 subtract 36, which is 12. So that's the answer, 12. Question 9. A padlock has 4-digit code. Each digit can be a 1, a 2, a 3, a 4, a 5, or a 6. For example, it could be 3662. The 4th digit must be an even number. How many possible codes are there? Now, when you've got selections like this, the number of selections you can find by working out each of the selections and multiplying it together. I normally start with the restrictions first. So let's think about the restrictions in this problem. We're told that the 4th digit must be even. Okay, so how many of those numbers that it can be a 1, 2, 3, 4, 5, or 6, except for this digit at the end. That can only be a 2, a 4, or a 6. Okay, so that means we've got 3 choices for that last digit. Now for each of the other digits, there are no restrictions. They can be any of those 6 numbers. So there's 6 choices for that one, 6 choices for that one, 6 choices for that one. So altogether then, there's going to be 6 times 6 times 6 times 3, which as a product of its prime factors would be 3 times 6 cubed. Okay, slightly neater way of writing it. Do you think we need to work it out? Debatable. If you've got a calculator, might as well. 3 times 6 to the power of 3. I make that 648 combinations. Well, that's that. I hope you found the video useful. If you did, please hit the like button and consider subscribing to my channel. Also, check out the playlist on the right for more topic tests, or the one down below for past papers. See you again next time.